Hello guys, welcome back to part 2 of the complete A2 physics guide. Last video, I did not like to stretch it out that long. However, today we're going to be catching up to our pace and hopefully finishing 5 more chapters in this part. I know I said there are a total of 4 parts in the previous video, but I'd like to finish within 3 parts and keep one last part for some examples and extra things that I'd like to teach you guys. Anyways, moving further, let's before I get started, I'd like to add something that is, so you know how I told you guys that uh, these are the these are the good papers, the good YouTubers with whom you can solve papers. Yeah, I forgot to mention one person. That is right. Sorry. Yeah, 8 CAIE paper solved. This person is from my country as well, and he's very, very, very good. Even though he has very few papers solved, his ones are amazing, especially for paper 5. P5 recommended. I know a lot of people struggle with paper 5, but he has a good amount of paper 5 covered for using which you by yourself can understand the pattern and can solve paper 5 by yourself just using the mark scheme. Okay, anyways, I think we are running out of time. No, actually, no, okay. Today, we're going to be going a bit more faster. So let's go. So what's our first topic? Our first topic is going to be chapter 6 oscillations, okay? Chapter 6 oscillations, or this is also known as simple harmonic motion. Okay, now let me draw the line so that we can distinguish between our concepts and our definition and structured question answers. There you go. I have to draw a big line. Okay, should be good. Yeah, nice. We are going to need this, trust, because simple harmonic motions is very big, and right, we can not select this. Excuse me. Okay, I think the line's made. Okay, let's start. So there are very few concepts, definitions and past paper repeated questions in simple harmonic motion. So first, okay. So number one is, of course, simple harmonic motion. Okay, simple harmonic motion is the motion in which acceleration is proportional to displacement. Uh, and acceleration is directed towards a fixed point. That's simple harmonic motion. Number two, what is forced frequency? Forced frequency. Frequency at which an object is made to vibrate. Number three is natural frequency. Natural frequency is frequency at which an object vibrates when free to do so. Okay. Number four is resonance. Okay, it is the oscillation of an object at maximum amplitude when driving frequency is equal to natural frequency of system. Basically, what this means is the oscillation of an object at maximum amplitude when natural frequency of the object is equal to the force frequency. Okay? simple. But the new syllabus prefers driving frequency and natural frequency. So yes. Okay. 5. We have angular frequency. We learned this in circular motion. That is 2 pi times frequency. Just this. Or 2 pi period. Right. 2 pi f. 6 is displacement. It is distance from a reference point in a given direction. Point in a given direction. 7 is damping. Okay, so what is damping? Loss of energy due to, excuse me, yes, loss of energy due to resistive forces. Okay, now we start our concepts. Okay, so simple harmonic motion. So I'll give you a basic concept, simple harmonic motion. That is, consider a pendulum. Consider a pendulum with a ball. Now, the pendulum can move this, can come back. We'll go here and then come back. Okay. The main concept of simple harmonic motion is acceleration is proportional to negative displacement. For acceleration is minus omega square x. This is the formula that we will be working with this entire thing. Now, a displacement. Displacement is okay. It's a displacement time graph. X naught is maximum displacement, minus x naught is maximum displacement in the opposite direction. So the formula for displacement is x is equals to x naught sine omega t. And maximum displacement is plus minus x naught. Okay. Now, how do we find out velocity? All right. Velocity, v, is dx by dt, basically the differentiation of distance, which gives us x omega cos omega t. V max is equals to plus minus x naught omega. Graphical representation is, excuse me, this okay, yeah, this is velocity. That was the distance time graph. This is the velocity time graph, where this is x naught omega and this is minus x naught omega. So the general equation is something. The general graph looks something like this. Okay. All right. Next is acceleration. Okay. Now, acceleration is the differentiation of velocity, which gives us minus x naught omega square sine omega t. And if you look at A max, you will see minus x naught omega square. Okay. Basically the defining formula of this chapter. Okay. Again, so this is negative acceleration. So acceleration time graph. Oh, my bad. Okay. So the acceleration time graph looks something like this. Sine graph in the opposite direction, where this is x naught omega, this is minus x naught omega square. Okay, all right. Now for some, now three graphs. Now what are the symbols representing these? Where? x is equals to displacement, v is equals to velocity, a is equals to acceleration, x naught is equals to amplitude, omega is angular frequency, t equals time. Okay, so our main equation, a is equals to omega square x, is the most defining formula of this chapter, as I said. Its graph looks like this. Acceleration, x, simply just a straight line to the origin. Now, when asked, we can say that you have to remember this. Particles in simple harmonic motion must fulfill this condition or satisfy this equation. Nice. Okay. That is the overall concept of simple harmonic motion. Now we move on to more advanced topics, that more advanced concepts that you will face when solving question paper. That is one being two, relating so you have to find the velocity. Uh, okay, you have to find the velocity of a particle at a certain point after it has been displaced from mean position. Okay, let me show you. So v and displacement x for particle performing simple harmonic motion. The formula for this is v is equals to plus minus omega x naught square. X naught is your amplitude minus x square. Okay, x squared. Okay, x is the displacement at any instant. Okay. Okay. Where omega is equals to angular frequency, uh, v is equals to velocity, x naught is equals to amplitude, and x is equals to displacement at any instance. Right. Now, to give you guys now, moving on to concept number 3. That is comparing displacement. Sorry, actually, I'm not gonna, yeah. Comparing displacement, velocity, and acceleration at various points for a particle performing simple harmonic motion. Okay, now let's think of a pendulum. This pendulum, there are 3 points. This is A, this is B, and this is C. At A, displacement is 0. At B, displacement is positive, is maximum at X, displacement is positive displacement or positive maximum displacement, which is amplitude. Or we can just say at B, X positive amplitude. At C, displacement is negative amplitude. At A, we have max speed. At B, V is equals to 0. At C, V is equals to 0. So as we have max speed in A, so V max is equals to plus minus x naught omega. Nice. Okay. Right. Right. Okay. And acceleration is max. Acceleration is max. So this one will be x naught omega square. This one will be minus x naught omega square. Now, this is the overall concept for this diagram, but I will break it down further into writing. For position A, which is the mean position, or which is the starting position or reference point, whatever you guys like to call it, our baseline. X is equals to 0, V is equals to maximum. Okay, V max is equals to plus minus x naught omega. Now, as A is proportional to X, therefore, if X equals to 0, A is equals to 0. For B and C, which are also known as extreme points, we can say a displacement is equals to X max, which is equals to, which is equals to plus minus X naught. V is equals to 0. Then, as A is proportional to displacement, therefore, if X is equals to max, A is equals A max is equals to plus minus omega square X naught. There you go. So this is another concept that you have to understand. This will all make sense once you guys start doing question papers. Trust me, there is nothing more that I can explain verbally than I'm writing down because there is nothing to explain. Okay, now moving on. Very important graph. Concept number 4. Velocity V against displacement X graph. It just does not stop, does it? Okay. Now, okay, now this is velocity against displacement. So the graph will look something like this. Okay, now, actually, let me align it nicely, right? Okay, so let's consider this point. Okay, this is velocity meter per second, and this is displacement meter. Okay, considering this point is plus x naught, this point is minus x naught, this point as maximum velocity, and this point as minimum velocity. Okay, 4 points. 1, 2, 3, 4. Now, basically, if my sketch might not be the perfect, but your sketch should give you guys a circle or an oval. Like again, guys, this is just a sketch. Cambridge doesn't always check your Cambridge doesn't check your drawing most accurately. So you just have to give them the idea that you understand what's going on. Okay, and there you go. Okay, that is this. Okay, now for next one. Five. Okay, formulas and graphs of kinetic energy, potential energy, and total energy for a particle of mass m or a particle of mass mkg performing simple harmonic motion. Nice. Okay. Again, let's copy this diagram for, oh, actually, I'll just redraw this diagram here because this will help us understand the concept better. Again, let's think of the pendulum. Okay. We have points A, B, and C. Now, at point C, kinetic energy is max because velocity is max. Kinetic energy at point B and C are 0 because velocity is 0. However, Potential energy at A is 0 because displacement is 0, and potential energy at B and C is max because they're the amplitude points. Okay. Now we know. So how to find out the kinetic energy if asked? Kinetic energy is half mv square. We know that for a particle performing simple harmonic motion, velocity is equals to plus minus omega x naught square minus x square. Okay. Now we can, if we substitute this v into this v, we will get half m plus minus omega root of x naught square minus x square whole square. Therefore, we'll get the equation kinetic energy is equals to half m omega square x naught square minus x square. Nice. Okay, this is the general formula of kinetic energy at any point. Okay, now I will double down on this concept. Okay, so the graph that we are expected to learn. Okay, right. See, okay, just before I draw anything more, like it's already so much. Right. Okay. So the graph that we're expected to draw, I'll draw it here. Okay. Right. Right. Okay, so this is going to be kinetic energy. Sorry, my bad. This is not kinetic energy, my bad. Wait. Yes. Right. Okay. And this is going to be this place. This is okay. The x-axis. This is the x-axis. This is the y-axis. Now we have few points. That is, we have negative amplitude and we have positive amplitude. Now, the total energy is equivalent. Okay, first of all, actually, let's draw the potential energy first. We know potential energy is 0 at amplitude. So at negative amplitude 0, negative amplitude 0. At 0, it's maximum. Maximum value is at 0. So, my bad. Right. So, potential energy at 0 displacement has a maximum value. If we plot the graph, we will see that it is something like 1 and 2. Similarly, kinetic energy kinetic energy is the opposite. Sorry. This is kinetic energy because kinetic energy at maximum amplitudes is 0, and kinetic energy is maximum at reference point or the baseline. Okay, now potential. Similarly, potential is opposite of kinetic energy. So at maximum point, at maximum amplitude, it has maximum value. At amplitude, it again has maximum value. And at baseline, uh, baseline potential energy is 0. So if we draw the graph, it becomes something like 1 and 2. Now, finally, what's the total energy? Draw a horizontal line from from the leftmost point to the rightmost point. Now, when all of it is together, this is your total energy. This is your kinetic energy, and this is your potential energy. Okay, just write it down for a better understanding. Ke is kinetic energy. Pe is potential energy. Finally, Te is total energy. Nice. Okay, thank you. Okay, a few more concepts are left, but we should be done soon. Okay, I'm just going to bring this out here. Nice. Okay. Nice. Okay. So, last time we found out the graph between kinetic energy, potential energy, and total energy, and we also find out how to find the kinetic energy of a particle in simple harmonic motion. Next, our next concept is going to be, okay, actually not, yeah, so the next concept is finding, all right, no, sorry, we're going to continue this. I think I'm going to put it all, the whole concept under this. Okay, let's see. Right, if not sure if I should, if I can do this. Okay, is everything copied? Hopefully everything is copied. I want to put it here. Okay, all right. I'll work with the space later on, but right now I've put it here because there's more things that I have to add on to this. Okay. Uh, I really hate the snap tool because so many things gets missed. Okay, guys. So now we found out how to find the kinetic energy. Now we're going to be finding out the how to find out the total energy and the potential energy. Now, note. I'll start off with note. No, total energy does not have a general or maximum formula. Okay. Rather, it only has one result. Some of you might ask what that is. That is uh, TE is equals to half omega m omega square x naught whole square. And this is constant for all particles in simple harmonic motion. Now, if this looks familiar, you guys are correct because this is the formula formula of Ke at position A. Okay, so basically, total energy is maximum Ke, or so it's equals to max Ke. Nice. Now, moving back on. So, moving forward, now we have to learn that how to find the potential energy. Now we know that, so basically, uh, okay. So basically, total energy is equals to kinetic energy plus potential energy. We can rewrite this as potential energy is equals to total energy minus kinetic energy. We learned from the previous formula that total energy is half m omega square x naught square minus kinetic energy is half m omega square x naught square minus x square. If we take half m omega square common, we will find x naught square minus x naught square plus x square. These two cancel each other out. Therefore, potential energy is equals to half m omega square x square, where x is the displacement at any point. PE at any x point. Okay. All right. So, at x is equals to 0, at x is equals to x naught, at x is equals to amplitude, P equals to max, PE max is therefore equal to half m omega square x naught square, which is also equal to the formula of the total energy. But yeah, so that's that. Now, finally, new concept, new concept. This is concept number 5. Okay, I think I'll like to give concept number 6 here. I want to use this space. The space looks empty and it feels bad. Okay, concept number 6. By the way, the remaining 3 concepts that I'm going to give you, just memorize the formula and the cases to solve any question, the question that correlates to this concept. Formula for time period and frequency of an oscillating pendulum. Okay, formula. Okay, this is it's a pendulum. So not gonna do the full thing, but you guys know the motion of a pendulum is something like this, this. Right. So yeah. So time period is equals to 2 pi root of length by g. Frequency is just the inverse, 1 by 2 pi root of g by L. L is length of pendulum, and g is equals to a is equals to acceleration of free fall. Right. Next, 7. This one's simple as well. This is formula of time period and frequency for mass attached for a mass attached to a spring oscillating in vertical plane. Oscillating in vertical plane. Okay, so, okay, all right. If we draw it, it's going to look like spring, mass. So this is mass, this is spring. Okay, and it's moving, sorry, it's moving up, it's moving down. M is equals to mass of particle. My bad. Where mass is M is equals to mass of particle. G is equals to acceleration of free fall. K is equals to spring constant. E is equals to extension of string. Extension of spring. Now, the actual formula is T is equals to 2 pi M by K. And frequency is, again, the inverse, 1 by 2 pi root of K by M. Now, we have another variation for this. T is equals to, sorry, made a mistake. Okay, no, I did it correctly, yeah. So another variation is 2 pi root of, right, actually, to just do it a little bit below this so that it doesn't look bad, right? So T is equals to 2 pi root of E to the E by G, and similarly, frequency is the inverse, 1 by 2 pi root of G by E. Nice. So that's not confusing. Right. Oh, actually, this is kind of confusing. So what I'm going to do is separate these two. Wow, why does it not work? Okay, I think it will work now. No, it's not working. Okay, nice. Now it worked. Okay, one here and another one here. Trying to neat out everything is kind of hard. Make sure that everything is neat and clean. Okay, okay, we got it. Nice. So one more, I think, is left. We'll call that concept. Okay, final one. We'll just do it here. That is, okay. Now this one, number 8, is formula for calculating time period T and frequency f for a mass attached with two identical springs. This is a very new case. I think we did not study this in AS. Okay, so the formula for this is, let me just draw the diagram first. So we have two spring constant. We have two springs. This is the mass, the other spring. Oh my God, I made a mistake. Right. Nice. Okay. T is equals to 2 pi root of n by 2k, and T is equals to, sorry, F is equals to 1 by 2 pi root of 2k by m, inverse. With this, we are done with simple harmonic motion, the chapter. Now, moving forward, our next chapter begins. That is, so our next chapter is electric fields. Chapter 7, electric fields. Right. Okay. So, electric fields, the definitions that we'll be going through are: one, electric field strength; force per unit positive charge; then we have two, which is field line. That is direction in which a positive charge will move. No. Three is electric potential at a point. Okay. So electric potential at a point is work done to move unit positive charge from infinity to a point. Four is Coulomb's law, which is electric force is directly proportional. Sorry, I think I crossed the line a little bit. Electric force is directly proportional to product of charges and inversely proportional to square of their separation. Number five is, it was a very rare question that I once found, I think in 2020 or 2021. Okay. No, actually I found it a few times. That is, what is indicated by the direction of an electric field line? The answer is direction of force on a positive charge. Direction of force on a positive charge. Okay, this is everything regarding electric fields. Now, I wish the concepts were as small as these definitions are, or these questions are. But no worries, we will still go through them. Yeah, okay. Again, time for line. Right, so no, I think this one should be fine. Yep, this one should be fine. No worries about it. Great. Now, why is it so slanted? The line is very slanted. Whoa, 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 whoa. No, actually. Okay, this should do. This should do. Okay. So, concept one. Now, before we start, the note is, I'd like to give a note. Electric field is very similar. Those concepts are very similar to gravitational field. Similar concept to gravitational field. And you will see so as we go along. First, Coulomb's law, or which is also known as the inverse square law. Okay, the Coulomb's law is force is proportional to product of charges and the square of their separation. Now think of this as a charge, and think of this as another charge, and think of this as the distance separating them. This is very similar to Newton's law of gravity, where force is proportional to product of masses and inversely proportional to square of their separation. Now, if we open this formula, it becomes k q by r square. This k is the constant of the medium. Constant of the medium. In A2, we only work with vacuum, right? Only vacuum in A2. Okay, now, for vacuum, k is equals to 1 by 4 pi E epsilon naught. Okay, where epsilon naught is electric permittivity, permittivity of free space, which is equals to 8.85 times 10 to the power minus 12 c square Newton per Newton meter, Newton per meter square. However, you don't have to remember the sole value because together you can just remember 1 by 4 pi epsilon naught is equals to 8.99 times 10 to the power 9. Therefore, we can say force is equals to 1 by 4 pi epsilon naught times QQ by r square. Where unit is Newton. Okay, this first concept. Now, concept number 2 is electric field strength, just like gravitational field strength, denoted with E. So the electric field strength E is equals to force divided by positive test charge. Now, okay, right. So again, I'll just draw a little bit of diagram. Uh, let's say this is capital Q, this is small q, this is the distance. Okay, if both of these are positive, okay, one force will act towards here, one force, the Q's force will act towards this direction. So what will be the electric field strength of capital Q on small q? So we know E is equals to 1 by 4 pi epsilon naught times QQ by r square divided by small q. Yeah, the Q's are cancelled out. Therefore, E is equals to 1 by 4 pi epsilon naught times Q by r square. Unit is Newton per charge. Unit is Newton per charge. Okay. Now, there's one more way to find the electric potential. Okay. Another way is across two plates. Sorry, electric field across two plates. Across two plates. Okay, across two plates. I'm just going to call this part 2 for electric fields. Let's call this part one. Okay, so part two. This is let's consider two parallel plates. The top one being 240 volts, the below one being 0 volts, and they have a distance d. They're separate by distance d. So electric field strength is voltage divided by the distance. Okay, now unit is volt per meter. Now, if we if we know that electric field strength is volts per distance, voltage divided by distance, and it is also is equals to force divided by positive charge. If we equate E is equals to E, then V by D is equals to F by Q. All right, then we can say force is equals to VQ by D. Force. Therefore, if we continue this, we know resultant force is mass times acceleration. So VQ by D uh, is equals to VQ by D. So acceleration of a charge is equals to VQ by MD. This is acceleration of test charge. Nice. Okay, now concept number three is electric potential. Same as gravitational potential denoted with V, but I think gravitational potential is denoted with phi. Okay, so V is equals to work done divided by positive charge. So we know that work done is equals to force into distance divided by positive charge. Okay, now we know that force is equals to 1 by 4 pi epsilon naught times Q by R square, and distance is also R divided by Q. So R crosses out, Q crosses out. Hence we get so hence we get V is equals to 1 by 4 pi epsilon naught multiplied by Q by R. Okay. Unit is volts. Unit is volts. Right. Or joule per coulomb. Okay. Now few concepts are left, not too many. For example, in electric fields, we have something called equipotentials. Equipotentials. This refer to line with same potential. Lines with same potential. Okay, lines with same potential are. So this is a positive charge. So this will have one, two, three. So it goes outwards. So it's an isolated positive charge. Negative. Two, three, four. Okay. Four. Towards. Isolated. Negative. Charge. And for across positive and negative, it's one, two, three, four. Outwards from positive charge, towards for negative charge. Nice. Okay. Then we have concept five, electric field lines. Electric field lines are, oh wait, I made a mistake. Sorry, guys, the mistake was, sorry, this is electric field lines. Okay, yeah, just this, messed it up. And five, equipotentials. Equipotentials are line with the same potential. Line with same potential. Now, for a line with the same potential, okay, it's going to be one, two. So this is a positive charge with field lines going outwards. Now, across this are the electric potential, and the lines crossing through it have the same electric potential, and it's called equipotential. So yes, nice. Okay, we have two more concepts left, and after that, this chapter will be done as well. So our sixth concept for this chapter is wait, excuse me, wait. Right, it is uniform field lines. Uniform field lines. Uniform field lines. So let's say there are two parallel plates. So this is 220 volts. This is 0 volts. V, this is, and this will be, okay. The field lines will go from high potential to low potential. I'll write it down. High potential to low potential. So that's that. Now, a few more concepts left. For example, okay, guys. So can you guys tell me? No, actually, you guys know that if potential is going towards the right, current flow occurs in the opposite direction. Direction of current flow. Right. Okay, now we have a few graphs to work with. These graphs are very important, and you have to understand their concepts. I will glimpse over them, but make sure you read upon them on your book or watch a further YouTube video to enhance your concept. Now, that is, okay. Okay, so let's say we have a charged metal small solid sphere. This is 7. This is 7. That's 7 graphs. Let's say we have charged metal solid sphere. Now, watch this. Okay, right. Let's say this charge particle is positive. Okay. Now, let's draw a graph around this. My bad. My drawing isn't as good as it used to be. Okay, nice. This is good. So this is the electric potential and distance, R. Okay, so electric potential and distance. So to till the surface, I have to annotate this a little bit. Okay, from the center. Okay, there you go. Okay, now actually a bit more. Right, okay. So, right, to set this up a little bit. Now, just do a rough sketch. Two graphs. One will be electric potential graph, and one will be electric field strength graph. Okay, this is R and this is E. This is electric potential, and this is electric field strength. Now, considering the surface of the charge, the electric potential has a constant value until the surface, and then starts to decrease in an inversely proportional manner. So we can say V is inversely proportional to R. Then, until this position, the electric field strength of the charged particle is 0. At the surface, it climbs to a maximum value, and then it starts to decline in an inversely proportional manner. This is because E is inversely proportional to R square. Right, now, okay, this is concept 1 for the graphs. Now, for concept 2, we delve a bit deeper. Now what we look at is, what we look at is between two charged, the graphs between two charged solid spheres. Two charged solid spheres. I'll draw the two graphs for electric potential and electric field strength, but afterwards I will give you some note points that I want you guys to just remember. I won't be explaining them because explaining them will take a lot of time. And our goal is not explanation, our goal is to complete the syllabus. Okay. Now, also, this is not a very big part of your syllabus, but I'm still doing it because I'm obligated to as your educator. So guys, the second part between two charged solid sphere are, you can see that these are the two graphs, one of electric potential and the other is of electric field strength. You guys have to learn to draw this depending on the situation, but this is the general graph that you have to know. I'm not going to go further explaining this. However, I'll give you some points that will help you understand this better because explaining this will require me to open up a question and draw four of these graphs separately, and four separate explanations is going to be a hassle. So I've prepared a little bit of notes which will help you guys. These two graphs, the first two graphs are very simple. They always come straightforward like this. But these two graphs, for number two, I'll okay. So take down these notes very carefully. The bullet points actually. Okay. So electric field strength. Electric field strength for like charges are in opposite direction. Then electric field strength for unlike charges are in the same direction. This is bullet point 2. Electric field strength, sorry, electric field strength is 0 when charges are like and opposite. Oops. I think I should wipe my just wipe my tablet screen because it's causing some issues. Okay, it should be good now. Electric field strength is 0 when charges are like and oops, opposite. Okay, this is for electric field strength. Now for um, so for electric field strength, I'd like to have near the electric field strength graph. Okay. Electric potential for unlike charges are in opposite direction. For unlike charges are in opposite direction. Electric potential for like charges are in the same direction. Therefore, electric potential is 0 when charges are like and in the opposite direction. Nice. So these are the points for electric potential and electric field strength that will come in handy when you guys face questions correlating to this concept. Right, now we'll move on to our next chapter. That is capacitance. This is chapter 7, no, chapter 8. Chapter 8, capacitance. As always, before starting this chapter, I would love to draw a big line. God. What do you increase it? Oh, there you go. There. Nice. Okay. We do have a lot of free space, but it's fine. Okay. Just wanting this to go a bit up. Okay, chapter 8, capacitance. So there isn't many definitions as well. I think this is one of the smaller chapters. I know I say this always, but believe me, this really is a small chapter. So 1 is capacitance. So the definition of capacitance is ratio of charge and potential difference. Ratio of charge and potential difference. You could say C is equals to Q by V. All right. So similarity and difference between gravitational and electric force field. Similarity and difference between electric and gravitational force field. So similarities are radial fields and lines normal to surface. Lines normal to surface. Difference হচ্ছে gravitational force is attractive and electrical force is attractive or repulsive. Force is attractive or repulsive or both. Whichever you can write both, you can write one, doesn't matter. Okay. 3. Function of capacitors connecting functions of capacitors connected in electrical circuits. Oh, sorry, I'm going to. This is a question that you write in bullet points. So, store energy, smoothing, blocking DC, then timing delay, then tuning, finally surge protection. Okay, 4. 4 is capacitance of parallel plate capacitors. This is C is equals to Q by V, where Q is charge on one plate and V is potential difference between the plates. Number 5 is field of a force. Field of a force. That is region of space where a particle, region of space where a particle experiences a force. 6. Oh no, I think that's it. So these are the 5 things that we have. Now time for concepts. So concepts of capacitance are very simple. The entire topic base concept or main concept is 1. Charge is proportional to a potential difference. Charge is equal to CV unit. Okay. All right. So unit of charge is Coulomb. Okay. Therefore, C is equals to Q by V unit Farad. F. I'll just write down what denotes what. Q is charge in one plate, charge in one plate of capacitor. V is PD across capacitor potential difference, and C is capacitance. Capacitors. Okay, nice. That's one. Two, factors affecting capacitance. The factors affecting capacitance are C is proportional to area, inversely proportional to distance. You can draw the diagram. This is the separation D, and this is, sorry, the R should be the other way. And this is the medium E. Therefore, capacitance is equals to E A by D, where C is equals to capacitance, E is epsilon is equals to electric permittivity in free space. A is area of capacitor, and D is the separation. D is distance between capacitors. Right. So this is all right. Now our next concept is very similar to something we've learned in AS, is series and parallel. Capacitors in series and parallel. Okay, so that is let's say this is okay. Right. Redraw this. So first we're going to look at series, capacitors in series. Okay. 1, 2, 3, 4. Now if I draw this correctly, this is one set of capacitors, two set of capacitors. Okay, so this is voltage, current, plus Q, minus Q, plus Q, minus Q. Okay, this is C1 by V1, C2 by V2. Okay, so we know in series, voltage is the sum of voltages, so V is equals to V1 plus V2. We know voltage is Q by C equals to Q by C1 plus Q by C2. Now, if we take Q common, Q by C, Q, 1 by C1 plus 1 by C2 cancels out. Therefore, 1 by C, therefore, 1 by C is equals to 1 by C1 plus 1 by C2. This is the formula of capacitance in series. Formula of capacitors in series. Okay. And we can further modify this by saying for two capacitors, C is equals to C1 times C2, C1 plus C2. And for identical capacitors, C is equals to 1 by N multiplied by capacitance of any one, multiplied by capacitance of any one. Okay, all right. Now for parallel. Okay, so let's draw the circuit first. Okay, oh my God. I think my screen's ruined. Okay, this is capacitors in parallel. Okay, this is current, voltage. This is I1. This is Q1 plus Q1 minus Q1 plus Q2 minus Q2. Actually, plus Q1 minus plus Q2 minus Q2. This is I2, right? Okay, so in parallel, we know that for parallel series, the total current is the sum of currents. in two regions. So we know the current is proportional to charge, so we can say it's also Q is equals to Q1 plus Q2. Now we know that Q is equals to CV. This is the voltage is constant, right? So C1V plus C2V, taking voltage as common, C1 plus C2, V cross. Therefore, capacitance in parallel R is C1 plus C2 plus Cn, right? Okay, right. Okay, so that is capacitors in series and parallel. Okay, there are a few more concepts that we have to go over. Okay, now next concept is okay, right here. So number 4 is energy stored in a capacitor. Energy stored in capacitors. And this is all very simple. Just in questions, you'll usually be given a graph like this. Okay, you'll usually be given a graph like this. Right. Label this V by V. Voltage against charge. Now, we know voltage against charge is proportional, so, oh my God. So the graph is going to be a straight line. Now, the area under the graph is equals to energy stored in capacitor. Right. However, you are always not going to be given the graph, so you have to you'll just be given values. So I'll tell you how to work it out with formulas. So we know that V is equals to work or energy divided by charge. It's the electric potential. So we can say um we can write it as work is equals to voltage into charge Q. Therefore, energy is equals to VQ. Right. Okay. There's more way to do this. For example, there are a few more formulas for the area. So we know area is equals to half into base into height. So we write half into V into Q. So therefore, E is equals to half VQ. Another formula for finding energy is, uh, so we know, so if we, uh, so, okay, first of all, we have, okay, we know E is equals to half VQ, and we know Q is equals to VC. If we substitute the Q with this, then we can get the formula E is equals to half V VC, then which is equals, therefore E is equals to half V square C, right? So this is another formula. And finally, a similar form in, okay, another energy formula is E is equals to Q square by 2C. You know, actually, if I write it like this, it becomes confusing. Another format is, uh, okay, now we can rearrange this into, right, yeah, we can rearrange this. We can write V is equals to Q by C, right? So if we substitute the V, then energy is equals to half multiplied by Q by C times Q, which is equals to half Q square C. Therefore, E is equals to Q square by 2C. It's another energy formula. Okay. Right. And one last, change in energy. So you can use any of the two formula. I usually prefer this one. To find change in energy, we can use half. We know capacitance is constant. Final voltage square minus initial voltage square. So that is the change in energy. Okay, that is that. And finally, okay, yeah, this is concept 4. So a few more concepts left. we finished concept number 4. Now moving on to concept number 5, that is capacitance of a metal sphere. This is also quite memorizative based, so you just have to memorize. Now let's say this is a metal sphere with radius with r, and it's positive. So let's just go positive around it. So it's positive charges around it. So we know C is equals to Q by V, that's 1. And V is equals to 1 by 4 pi epsilon naught into QR is our equation 2. Now, through substitution, we can say C is equals to uh, Q divided by 1 by 4 pi epsilon naught multiplied by Q by R. So Q cancels out. Therefore, capacitance of a metal sphere is 4 pi epsilon naught R. And from this relationship, we can say that C is proportional to R. Now, that's concept number 5. Concept number 6 is discharging of a capacitor. Discharging of, this is very new. This is added from the 2022 syllabus and onwards. Okay, so let's draw the discharging circuit. It's power supply A and B, A, B, right? Okay, so this is a resistor. Okay, this is power supply 2, 3, 4. Okay, this is an ammeter right here. Another point here, another ammeter. Okay, now let's just draw a capacitor here and here. So this is minus and this is plus. Okay, now, all right. So the left side is charging, the right side is discharging. Okay, now it's very simple. Basically, you have to follow a few formulas. I'll explain them, but first I'll draw the graphs. There are total 3 types of graphs that you are required to know. But the general idea or the general sketch is the same across the 3 graphs. Okay. I have to work on my drawing. Okay, so this is charge by time. Okay, now there are 3 types of graph. All of them have the same general sketch. Watch. So this is maximum charge, and this is an exponential decrease. So okay, wait, I can draw it better. So this is an exponential decrease. Now, literally, wait, can I not copy it? Does this tool not have a snip? This is why I don't like. This is the reason why I don't like uh Microsoft OneNote. Wait, I have a better idea. So only 3 graphs. Right. Okay, 3 graphs. Watch. Nice. Okay, so 3 graphs. One is for charge, one is for voltage, and one is for current. You can also have one graph for resistance, but anyways, the general idea is the same. So Q naught, V naught, I naught. This is the general shape of the graph. It's called an exponential decrease. So we can say charge, voltage, and current. Charge, voltage, and current decrease exponentially with time. Nice. Okay, what else is left? Oh, right, now for the formulas. So the formulas are Q is equals to Q naught, e to the power minus t by time constant. V is equals to V naught, e to the power minus t by time constant. And I is equals to I naught, e to the power minus t by time constant. Therefore, general discharging equation is X is equals to x naught. Sorry, x is equals to x naught e to the power minus t by time constant. Huh. Where where uh x can be charge, current, voltage, resistance, x naught, initial values, t is time, uh this is time constant, and finally c is capacitance. Oh, holy guacamole. Okay, no. Right, C is capacitance. Now, uh, final concept that is left is this is the most new thing that in our syllabus that I think you guys have seen because we've never encountered this in either AS or IGCSE O levels. Okay, so right, so final concept is concept number 7, that is time constant. Time constant. It is product of resistance and capacitance. Even though this should have been in the notes section, I've never seen the definition of time constants ever come. So I just wanted to give it to you guys in the concept section as a note and a reminder so that you guys don't forget. So time, okay, so we can just write time constant goes to R into C. Unit is seconds. Yes, that's it. That's actually to snip this out. I'm going to take it here because it's taking too much space. Okay, so yeah, that is our chapter 8, capacitance. This one was long, but not as long as simple harmonic motion.